Okay, so for the exam one review, it's chapters 1 through 10, or sorry, no, it's 1 through 4. I don't know where 10 came from. So chapter 1, remember that's one folder, and then chapter 2 and 3 I combined into just its own folder. So that was, a lot of content in there. And then chapter 4, this last chapter. But those 4 chapters are going to be covered on this first test. You can see on the review sheet, there's 36 questions, it's 200 points. And then what I did is my courses is problematic for me in a couple of ways. And one of the ways is if you give a test, it's very hard to say that this particular question is going to come out as bonus points. And so what it'll do is it wants to calculate all the possible points and not just have one question be a bonus question. So the workaround, which is not great, obviously, but the workaround for me is to just create an entirely separate quiz, the bonus quiz. So what I don't want you to forget to do is after you take your test or before, you can do it with however you want to do it. Don't forget to go in and do the bonus quiz. And the bonus quiz, I know I put on here that it's 5 points, but it actually has 2 5-point questions. So it's actually worth a possible 10 bonus points. This is a 200-point exam. I normally give 5 points out of 100. So 5%, it would be 10 points out of 200. So I went ahead and gave 2 questions. They are written response questions, which means you have to, it's not multiple choice or anything like that. You got to show your work, give all of your answer in the space provided, and then I will get that graded. With the test 1 itself, not the bonus test, but the actual test, it is a mixed format. Some of the questions will be fill in the blank, like you maybe saw on previous practice quizzes. Some of them will be multiple choice. Some of them will be written response where you have to type in your answer. So, it's a little bit of everything, I guess. Your periodic table will be included in the test. So your periodic table, in fact, I think I posted it like 2 or 3 times, not to be redundant, but just to sort of prevent all the scrolling way back to the beginning, right? So, because that can be kind of annoying if you're taking a test and you keep on having to scroll and scroll and scroll. So I think I posted the table at the beginning of the test and then again in the middle, and then I may have done it may have done it a third time, but I'm not sure. I may have talked myself out of that. Anyway, so with the periodic table, make sure and this is like a nice review from intro, make sure you know your family names, the charges you expect on ions. So for example, lithium, sodium, potassium, cesium, not hydrogen, but the other 4 that I just named, lithium, sodium, potassium, and cesium, right? Those are your alkali metals. Next door, magnesium, calcium, strontium, barium, radium, those are your alkaline earth metals. Hydrogen here is an exception to the left of the metalloid stair step. It is a non-metal, so it's not a metal, it's the exception. Then in the middle, we've got our transition metals, right? From scandium to zinc, right down to mercury, right? This like middle 10 block right here, that's your transition metals. And then as we go past the transition metals, we get to that metalloid stair step. And the metalloid stair step, right, it goes between boron and aluminum, and then aluminum down to through silicon, and then over, down. And typically your metalloids are the ones that border that stair step, which makes total sense. This is the boundary that separates our metals and our non-metals. So it makes sense that the elements along that boundary are going to be metallic and non-metallic in their behavior and in their bonding, and sort of depending on, what they're partnered with, et cetera. So those are metalloids, right? And the exception here is the aluminum. Aluminum is a true metal, but boron, silicon, germanium, we don't have to know. Arsenic, antimony, tellurium, polonium, we also don't have to know these 2. But the 4 that we have named that we should know, antimony, arsenic, silicon, boron, those are your metalloids. Then below the stair step here, right, kind of aluminum, tin, lead, bismuth, those are just metals, no special name for us to worry about. Then we got our noble gases all the way at the end. And then of course our halogens, fluorine, chlorine, bromine, iodine. So your family names, no big surprises there. Then atomic structure, protons, neutrons, and electrons. Hopefully this is, a good review from intro. But if I just pick an element, let's say chromium, right? So chromium, and let's go ahead and talk about the atom of chromium, all right? Atom, of course, means that it's neutral. There's no charge. So these 2 go together, right? 0 charge overall. And I know that because the atomic number is 24, it's going to have 24 protons in the nucleus. And then because it's an atom, that also means it's going to have 24 electrons outside the nucleus, because if an atom is neutral, the positives and the negatives have to cancel out. The mass number underneath, 51.99, that would round to 52. So we take that mass number of 52 minus the atomic number of 24, and that'll get us our number of neutrons. So for the chromium atom, we expect 24 protons, 24 electrons, and then 28 neutrons. Now, if we were going to do the ion of chromium, the problem with the ion of chromium is that the charge can be different. It's not like it's always a +2, right? It can be a +2, +3, +6. So I would have to tell you, okay, let's look at the +2 chromium ion. And now let's look at protons, neutrons, and electrons and see what we find. Now, the proton count, that will always be 24. If it's chromium atom or ion, period, it's always going to be 24, because of course that's the atomic number. And if we're not changing the mass number, if we're still going to use the 52, then we're still going to have 28 neutrons in the nucleus. Those are my two heavy particles in the nucleus, the protons and the neutrons. Now with the electrons, what we want to remember is that if it is a positive ion, like we have here, the electrons have been lost, right? You've lost negative. So you basically, the way I think about it is I have two more positive particles than negative particles, right? And so overall I have a positive 2 charge. So if it's a +2, you've lost 2 electrons. So instead of 24 like we expected in the atom, we're only going to have 22 in the chromium +2 ion. All right, so that's how we do protons, neutrons, and electrons for an atom or an ion. That hopefully is a pretty nice review from intro. Next thing, if we look at significant figures, just remember your rules. If you're multiplying or dividing, make sure you just look at least number of sig figs. If you're adding or subtracting, make sure you follow the decimal place. And then also remember, if you're doing a temperature conversion, you follow the decimal place rule. So whatever temperature you're given, if it goes to the ones place, when you convert it, keep it to the ones place. If the original went to the tenths place, then you keep it to the tenths place. Now the prefixes, we had 3 last semester that we used quite a bit, the kilo, centi, and milli, and I've added 3 more for this semester. We've got the big M for mega, which is 10 to the 6th, the curvy U, I guess, I'm sure there's probably a fancier title than that. That's micro, 10 to the -6, and then nano, to me, it always sounded like 9, right? So it's 10 to the -9. So an example for that.
Professor,
Yeah, go ahead.
I have one question. Going back on the sig figs for temperature conversions. On one of the practice quizzes, it was converting -109 Fahrenheit to Celsius.
Okay.
The correct answer was -78. And I think I kept putting -78.0. Why is it -78 again?
Yeah, the reason is because you're losing a sig fig, but it's okay because what we're following is the place with regard to the decimal. So since the 109 only goes to the ones place, nothing past the decimal, we're going to do the same thing when we do our temperature conversion and not put anything past the decimal. So rather than thinking about sig figs for temperature, that we want to follow the decimal place. The idea, I think, is that if the thermometer could only read to the ones place, then when we convert, we're going to keep that only to the ones place. We really don't have enough precision with the thermometer to convert that to the tenths place, because we didn't have that originally. Does that make sense?
Yes. Yes. Okay. I see.
All right.
Now.
Very
Thank
good.
you.
Yeah, you're welcome. It's a good question because it comes up a lot. It's like the one decimal place, like sig fig rule, that I always see a partial deduction for quite a bit with the temperature conversion. So it's like got its own special rule. Now with the prefixes that we were talking about, something like this, like if I said, okay, 5.8 times 10 to the 6 grams, what would be the prefix to replace 10 to the 6? And that would be mega. So make sure you know mega is 10 to the 6, kilos 10 to the 3rd, centi 10 to the -2, milli 10 to the -3, micro 10 to the -6, and nano 10 to the -9. And those are all back in the module, or not module, chapter 1 folder. Now the unit conversions, there were, most of these were the same as what I had my face-to-face students learn for intro. So for example, like 1 inch is 2.54 centimeters. The milliliter and the cubic centimeter are equivalent. The kilogram is 2.205 pounds. But the new one, I think that I actually end up using quite a bit for some reason, is that a gallon is 3.785 liters. So make sure you have those memorized. And then be able to determine the density of a liquid or a solid. And these were definitely on the practice quizzes for this chapter, where I would give you the information, the mass and volume measurements, and I would ask you to determine density. And the only thing I think you have to just be careful about here is that, because a lot of times you're getting either the mass or the volume by difference, right? You're going to subtract final minus initial. When you do that subtraction step, make sure you follow the decimal place. And then when you do the division to get density, then you look at your significant figures. Now, nomenclature for me, that was, I'm not a memorizer. So nomenclature for me was the part I always had to sit and spend a little time on, which is probably why organic was not my favorite of the chemistry courses, because it's a lot of memorizing. But the polyatomic ions, you want to memorize those. I'm going to review some of those today. And of course, the element names and symbols that are also posted, there's a list in that chapter 2-3 folder. Now, in that folder, this is where we began some stoichiometry, in the sense that we got into our mass, mole, molecule, and atom conversions. We also looked at percent composition questions, empirical molecular formula. Excuse me, my allergies are bothering me. Then the only kinds of reactions that we have to worry about for this first test, we've got combustion, which I'll review here in a little bit. And then what do the alkali metals like sodium, what do they do with halogens, oxygen, and water? And I've got reviews coming for that. And then of course we got into some stoichiometry. Nothing extra, like no molarity yet. We haven't gotten into that yet, but we have. So yeah. Yeah, I hope so too, Trudy. I hope the rain takes away all of the pollen. So the stoichiometry, we're just basically looking at mass, moles, molecules, and atoms. So we don't have to worry about molarity conversions just yet, or gas conversions just yet. That's coming. What is a little bit different here, I think, we saw limiting reactant in introchem. We saw percent yield, but we didn't do excess reactant. So that's just adding kind of another layer to stoichiometry. And I have some examples coming. So my plan was to work through the practice problems today. And then if that brings up any questions for you, please let me know. But that's what I'm going to start with. All right. And first question, it says we want to know the molar mass of copper 2 chlorate. And then I put on there tetrahydrate. All right, so kind of an opportunity to not only review molar mass, but also nomenclature, right? So when it says copper 2, we know that that means copper has a +2 charge. The chlorate, 8 always makes me think polyatomic ion, not ide, right? If it were chloride, we would just be looking at Cl. But chlorate is ClO3 -1. And my computer froze again. I don't know why it always does this. So what I need here is 2 of those -1 chlorates, right? I'm going to have 2 of those to balance out my 1 copper. So what I'm going to do is have Cu, just 1 Cu, and then 2 ClO3 chlorate polyatomic ions. And then with the hydrate, right? Hydrate means water, and tetra means 4. So at the end here, we've got that little dot and then 4H2O. So copper 2 chlorate tetrahydrate is CuClO3 2.4H2O. So the first thing I was asked for in the review sheet was, what is the molar mass of that? And if you're just asked for molar mass, then that just means go to your periodic table and get all the stuff you need. So copper, I always do 2 decimal places, but feel free to go more than that. Just don't do less than that. So 63.55. Chlorine is 35.45. Oxygen is 16.00. And then we have hydrogen, and I go 1.01. All right. Now what I want to do is go back up to my formula. I only have 1 copper. All right. So just 1 of those. So just 63.55 for the copper. For the chlorine, distributing through the parentheses, I've got 2 of those. So 35.45 taken twice would be 70.90. Now the oxygen, I have 6 in that chlorate first, the 3 times 2, so 6 oxygens there, plus another 4 in the water molecules. So I have actually a total of 10 oxygens. So I have 160 grams total for the oxygen. And then for the hydrogen, I have 2 times 4. So I have 8 total hydrogens. So I have a total of 8.08 for those 8 hydrogens and the 4 water molecules. So when I add all of that together, I'll get my molar mass of the copper 2 chlorate tetrahydrate. And the number I get here is 302.53 grams per mole. All right, so there's my molar mass. Then the second question we were asked for this example was, how many, whoops, that was 1, not A. I got ahead of myself. Now we're doing A. All right, so question 1 was just finding the molar mass. Sorry about that. For question A, it says we have a 575 gram sample of the copper 2 chlorate tetrahydrate, and we want to know how many moles that would be. All right, so we know that if we're converting between mass and moles, we need the molar mass to do that. What we just figured out was 1 mole weighs 302 grams roughly. So how many moles would be in 575 grams? Now your constants, right? Your periodic table, your molar mass, right? Those are always your conversion factors, right? Anything that's a constant like that. We know copper 2 chlorate tetrahydrate, the molar mass is always 302.53. That's always what you use as your conversion step. So we start with our 575 gram measurement that we were given. We know we want grams on the bottom to cancel out and moles on top. So that's our molar mass of 302.53 grams per mole. So when I divide that through, keeping 3 significant figures, I get 1.90 moles. All right, so if you're being asked for moles, that's all you got to do there. And I think a lot of times when students are asked for moles, they want to take it a step further and go to molecules. But if you're going to moles, you're going to like that center point. You only have to get, if you're starting with mass, just your molar mass to take you to moles. The next question, though, will go an additional step. It's asking now, how many molecules would that be? And so you want to remember that in order to go to particles, you need Avogadro's number, right? And you want to remember this number, 6.022 times 10 to the 23rd. And that is the number of molecules in 1 mole. Now, the problem with Avogadro's, it's not really a problem, but a little bit, is that the particle type depends on the substance that you're talking about. So, for example, if I was doing this question and I was just looking at copper, that's all I was looking at was just copper, then what I would do here is my particle type would be an atom, right? Because copper is an element, so you have atoms of an element. But I had the copper 2 chlorate tetrahydrate, right? And so that, of course, is a molecule. So that's why I'm using molecules here. All right, then I'll take my 1.90 times 6.022 times 10 to the 23rd, keeping 3 significant figures. I get 1.14 times 10 to the 24 total. Nope, that has to be a 23. I don't know. Oh, no, that's right. Never mind. 24 molecules. All right. All right. And then the last part here is, what if we wanted to break it down an additional step and look specifically at oxygen atoms in the sample? So what we've determined at this point is we have 1.14 times 10 to the 24 molecules of this copper 2 chlorate tetrahydrate. And what I want to break this down into like an additional step is to look at each individual molecule and figure out how many oxygen atoms are in each of those molecules. So when I look at one molecule, and this is what we did when we did our molar mass calculation, we had 6 oxygens in the chlorate groups and then another 4 in the water molecules. So we had a total of 10. So we end up here at 1.14 times 10 to the 25th. And yet I still wrote a 4, sorry, oxygen atoms. All right, so that's how we can take it an additional step to break it down into a specific atom. And the 10 obviously is unique to this formula. If instead we were looking at chlorine atoms, if we were just looking at chlorine, then we would only have 2, right? So 2 chlorine atoms per molecule. If we were looking at hydrogen, 4 times 2 would be 8, right? So 8 hydrogen atoms per molecule, all right? So hopefully that helps review mass, mole, molecule, and atom conversions. The next question, we're looking at percent composition of zinc acetate. And again, trying to review nomenclature as much as I can. Zinc acetate, I know zinc, right, is Zn. I know it's a metal, so it's going to be an ionic compound. And I know that zinc on that diagonal on my periodic table, I know it's a +2. Aluminum 3, zinc 2, silver 1. Excuse me. Then acetate, another 8 polyatomic, C2H3O2, which is a -1 charge. And to get those charges to cancel out, kind of like we saw with the copper and the chlorate in the earlier example, I'm going to need 2 acetate groups to balance out the zinc. All right, so now I have got a -2 balancing out my +2. So if we're doing a percent composition question, what we want to basically do first is find the molar mass. So again, I've got zinc, carbon, hydrogen, oxygen. All right, and then I go to my periodic table. Zinc has a molar mass of 65.41, carbon 12.01, hydrogen 1.01, and then oxygen 16.00. I only have 1 zinc, so 65.41 grams for the zinc. Now with the carbon, I've got 2 in the parentheses times 2, so a total of 4. So 48.04 grams for the carbon. 3 hydrogens per parentheses times 2 means I've got 6 total hydrogens, so 6.06 grams for the hydrogen. And then 2 oxygens per acetate times 2, so a total of 4 in the oxygens, so 64 total from all 4 oxygens. So 64 added to 6.06, added to 48.04, and then added to 65.41. I get a molar mass of 183.51. All right, now if we were doing percent composition of all the elements, then we would just go through for each one, take the mass of that element, divide it by the molar mass of the compound times 100. But specifically for this question, I just wanted to know the percent of carbon. So if we're looking just at carbon, we want the mass of all 4 carbons. So we had 48.04 divided by the mass of the compound, the 183.51, and then times 100 to get it into parts per 100. All right, so the answer I get here, I always keep 2 decimal places, not because we have any sig figs to go by. That's just what I always did, is just keep 2 decimal places. So I got here 26.18% for the mass percent of carbon in zinc acetate. All right, so hopefully that looks familiar from intro chem, but that's just percent composition. Now, the reason why we have to learn percent composition is because we have machines that can give us percent composition data, and we have to take that data and then figure out what the empirical formula is. So that's going to be the next question. So let me move this, go to my next page. All right, let's see, I'll keep that up there in case anybody's still using it. So for number 3, on the review, it tells us that we have a compound that is 34.31% sodium and 17.93% carbon and 47.76% oxygen. And the molar mass is 134. And we want to know the empirical formula first. All right, so when you go through your empirical formula, you have to start with the mass of each element. Now we have a mass percent, which is great. We're just going to assume 100 grams, and that means we have 34.31 grams sodium, 17.93 grams carbon, and 47.76 grams of oxygen. So you always have to start with mass first to do your empirical formula. If in doubt, where do you always go first? You go to moles, right? It's the chemist center point of everything, just about. So we're going to divide by the atomic mass from the periodic table, 22.99 for sodium, 12.01 for carbon, and then 16.00 for oxygen. So 34.31 divided by 22.99. I have 1.492 moles of sodium here. 17.93 divided by 12.01. I have 1.493 moles of carbon. And then 47.76 divided by 16. I have 2.985 moles. All right, now that is the mole ratio. It's just those are not pretty numbers to make for subscripts. Like we're not going to write a formula that says Na subscript 1.492, right? So we want to make these prettier. And so we simplify, but this is a fixed ratio. It's just like they're just not whole numbers, right? But for every 1.492 moles of sodium, there's 1.493 moles of carbon. So the reason for saying that is once you have your moles of each element, whatever I do to one column, I have to do to all of them, right? This is my fixed ratio. It's just not, they're not nice numbers. So what we do to simplify is we divide by the smallest. When I look at my three numbers of moles, my sodium was the least. All right, so we're going to divide everything through by that 1.492. And of course, that forces the sodium to go to 0. That makes it easy. Let's see exactly what the carbon comes out to be, but it's going to be a 1. But let's see, it's 1.001. And then for the oxygen, I get 2.001. All right. So at this point, you might need a multiplier, right? And the only time that that happens is if one of these that we just solved for after dividing by the smallest, if it ended in like a 0.5, like just hypothetically, let's say that this had been 1 to 1 to 2.5, a 0.5 would mean that your multiplier should be a 2, right? Because 0.5 is a half, that makes sense. If you had a 0.33 or that 0.33, right, that's a third, so multiply by 3. And a 0.25 is a quarter, so that would mean multiply by 4. In this case, we didn't need a multiplier because everything turned out to be a nice whole number. So we have our empirical formula. This compound is NaCO2, right? And that's not the true compound, that's just the ratio. It's what I know so far about this is that every time there's one sodium, there's one carbon and there's 2 oxygens. So I know that at least that's sort of the generic structure, but I don't know exactly what the compound is. And I have to have another piece of information given to me to know exactly what the true molecular compound is. So that other piece of information we were given in the question is that it said that the molar mass of the true compound was 134 grams per mole. All right, so the way that I think about empirical formula is an empirical formula is a repeating unit. So it's like a chunk of the compound that repeats exactly like that. So like I could take NaCO2, repeat it again, and it would be Na2C2O4. Or maybe I repeat it again, Na3C3O6, right? So what I want to figure out is in that empirical unit, right, how many times does it repeat? Once, twice, 3 times, 4 times, right? Until we get to the true compound formula. And what we know about the true compound formula is that the mass is 134 grams per mole. So what I want to figure out is what is the molar mass of my empirical unit, my repeating unit. So that's actually what I'm going to figure out next. So sodium 22.99, carbon 12.01, and then 16 for the oxygen, but taken twice. So I've got 32 plus 12.01 plus 22.99, and I get 67 grams per mole. So what I can see here is that 67 goes into 134 twice. So it has a factor of 2. So that tells me that my empirical unit repeats twice until I get to the true molecular formula. So that molecular formula, instead of only having 1 sodium, would have 2. 1 carbon becomes 2, and 2 oxygens becomes 4. So Na2C2O4. And then the last thing I asked you to do was to name this. Just again, practice nomenclature while we're here. We know Na is sodium. We know sodium is a metal. With metals, the question is always, do I need the Roman numeral? And you can look at your periodic table and say, no, because sodium is always a +1, right? Alkali metals are always +1. So it would be redundant. We don't have to say sodium 1. We just have to say sodium. And then this big thing after that, the C2O4 is a polyatomic ion, and that is called oxalate. All right. So that would be our name for this compound, sodium oxalate. All right. So we did our percent composition to an empirical formula and then figuring out what the true molecular formula is. So now if we go to number 4 on our review, it says it wants the balanced combustion reaction for octane. All right, so we're going to do a combustion reaction. What you always have to have for combustion, right, the fuel for the fire is the O2, right? You have to have that. The hydrocarbon has to bond with oxygen or react with oxygen from the air. And the two products in a perfect world, we talked about this, the world is not always so perfect in many ways, right? But in combustion, when we talk about combustion reactions, we're assuming a complete efficient burn. All of the carbon comes out as carbon dioxide and all of the hydrogen comes out as water. And both of those are in the gas phase because of the heat. The water's coming out as steam, right? So when I go to balance, all I really would say here is save oxygen for last. It splits, right? So do that one at the end. If we do carbon first, there's 8 carbons in the octane, only 1 in the CO2. So multiplying that by 8, now I have 8 carbons on both sides. I've got 18 hydrogens in the octane, but I need the multiple of 2 to get me to 18. So I'm going to put a 9 in front of the water. Whenever you have an odd number in front of water, you're going to have an odd number of oxygens, which means this is going to have to be a fraction in front of the O2 or a decimal. Frankly, I'm fine with that, but it's going to want whole numbers. So it's up to you. Like if you're typing it in written response, feel free to leave it as a fraction or a decimal, but a lot of students like to have whole numbers. So I'll show you both and you pick which one you like better. All right. If I want to stick with a fraction, what I'm going to do is sum my oxygens. The carbon and the hydrogen should be balanced on both sides now. But with the oxygen, I have 8 times 2. So I have a total of 16 in the carbon dioxide, plus another 9 times 1. So 9 in the waters. So I have 25 total oxygens on the product side. And I want 25 on the reactant side. So what you can do here is say 25 divided by 2. Because what you can see is the 25 divided by 2 times 2, those 2's are going to cancel out. However, a lot of students will say, well, then why can't I just write 25O? And you can't because oxygen doesn't exist as O, right? It's one of our 7 diatomics. It always exists as O2 in its elemental form. So that's why you can't just write 25O, even though that logically makes sense. You have to write it as O2 because that's how it appears in nature, right? And then we just take 25 divided by 2 because we're multiplying it by 2. And now we have our 25 O's. Or if you prefer whole numbers, then we would have a 2 in front of the C8H18. Just start over, multiply your hydrocarbon by 2. We'll come back to the oxygen here in a second. Instead of 8 CO2s, we'd have 16. And instead of 9 waters, we'd have 18. All right, and now if I look at my oxygen count, I've got 32 here in the carbon dioxide, plus another 18 would be 50. 50 divided by 2 means a 25 in front of the O2. So it's the same equation. We've just simplified, or we've taken away the fraction, right? That's it. But otherwise, it's the same. So then the follow-up to this says, all right, we've got our balanced equation now. If 275 grams of the octane reacts with 525 grams of the oxygen gas, which one is the limiting reactant? All right, and so you may have seen these questions on the chapter 4 practice quiz. When you're only being asked which one is limiting, what's I think hard about that is that it's not a specific endpoint. You know, it's not like we're saying, okay, how many grams of water are we going to make, right? We're just saying which one's limiting. So when that happens, when you're asked for that, just which one is the limiting reactant, your answer is going to be either O2 or octane, right? That's all we're doing. We're trying to identify the reactant that runs out first. So your answer is either going to be octane or O2. What I kind of think of is for each of those 2 reactants, how many reaction cycles could each one accomplish? That's kind of what I think about. All right, so what you would do is you'd start with your first reactant, 275 grams of C8H18. We know it's a mass. We know always in chemistry, right? We go to moles first. So 8 carbons at 12.01 apiece, plus 18 hydrogens at 1.01 apiece. I get 114.26 grams. All right. Now, if I look at the oxygen next, we had 575 grams of O2, 1 mole of O2, 2 oxygens, so 32.00 grams. Now, we are not done yet. And this next step is the step a lot of students forget. We've gotten to moles of each, but what we have to take into account is that every time I use 2 moles of octane, I need 25 moles of O2. So I need a lot more O2 than I do octane.
So, Professor, excuse me, I think it's is it 525 or 575?
Oops, sorry. Yep, it is 525. Thank you. I was looking at the 275 and mixing them together. Okay, so the step here that you don't want to forget is that I only need 2 moles of octane every time I do this reaction, but I need 25 moles of O2. So what the system has you do, because this is the way Dr. Musgrave always sets it up, is he just put a 1 on top. And then for the octane, you need 2 moles of C8H18. And then for the oxygen, you put a 1 on top and then 25 moles of the O2. All right. I know a lot of students, sorry, they don't love just putting a 1. And I can't blame you. Like it's taught when we begin our unit conversions to cancel out our units as we go. And it seems odd to just have something that doesn't have a unit. So when I was doing this in the video, I would say, okay, I put cycle on here. Like every time I do 1 reaction cycle, I need 25 moles of O2. Every time I do 1 reaction cycle, I need 2 moles of octane. If that makes sense to you, then feel free to write that in. The system is going to say, I don't like cycle. It's going to mark it wrong, and I'm just going to go back in and fix it. But if you want to leave it without a unit on top, just put a 1. That's fine. That's what the system's looking for. But again, a lot of students are like, how can it not have a unit? And I can't disagree with that, right? So 1 cycle needs 2 moles of octane. 1 cycle needs 25 moles of O2. But just don't forget that step, because that's important. There's a very big difference in those molar coefficients. If we forgot that, we would probably get the wrong limiting reactant. Okay, so the 275 grams of octane divided by the molar mass of 114.26, and then divide by that coefficient of 2, I get 1.20 cycles. Right. So I have enough octane to basically go through 1 1/5, 1.2 cycles. For the oxygen, 525 divide by 32 and then divide by 25. I have 0.656 cycles. So I don't even have enough oxygen to go through 1 full reaction cycle, right? Only 0.656, and then the reaction stops because the oxygen's gone. So at this point, we circle the smaller. That's not the answer, though. It just helps us identify the answer. Remember, if it's asking you which one is the limiting reactant, you're going to be naming a substance, right? Your 2 options for this particular equation is either going to be the C8H18 or the O2, right? Those are your only 2 reactants here. So it's either one or the other, right? Which one's limiting? And what our calculation showed us is that oxygen runs out first. So that's going to be our limiting reactant. All right. And what we know, because this is going to segue into what's going to be coming soon, is that if one reactant is limiting, that means the other reactant will be present in excess. Right. So if one runs out first, that means we still have a little bit of the other one left over. All right. So hopefully that was a nice review of combustion reactions and a little bit of stoichiometry, just identifying which one the limiting reactant is. So the next example I have is a different type of reaction. So let me move that down in case I went too quick. All right, so for number 5, we have the balanced chemical equation for the reaction of lithium solid with iodine solid. All right, so it's asking for lithium and iodine. All right, so there was a pretty good amount of reactions with alkali metals specifically in this. Like those are the only two types of reactions we really have to worry about for this first test: combustion and then reactions with the alkali metals. And both of these come under the category of redox. So what you want to make sure and kind of imagine here, when it talks about lithium solid, it is talking about elemental lithium, which means there's no charge here. We're so used to saying, oh, lithium, alkali, +1, right? In a compound, that is true. But when it's talking about lithium solid, that means that we're talking about lithium in the elemental form, right? And so it's just lithium, not an ion, but as an atom. When it says iodine, right, not iodide, right, but iodine, then what we have to remember here is that iodine is one of our 7 diatomic elements. And so it's going to show up as O2. And again, that is the elemental form of the iodine. So your 7 diatomics, right? You remember your Hofbrinkel. All right, now lithium, right? Not on that list. So lithium is singular, but iodine is an I2. So for these 7 elements, when they're in their elemental form, not as ions, they're always diatomic. Now, when I put these two together, right, it's going to make lithium iodide. It's going to make an ionic compound. And now we can go back to thinking about what we normally think about, which is lithium is a +1, iodine is a -1. The 2 subscript on the iodine does not carry over, because over here, this is on the reactant side, I2, all of its electrons are intact. It's an elemental form, so that's where it's diatomic. When it comes over to the product side, it's now turned into iodide, the ion of iodine, with a -1 charge. And of course, the ions are always singular, unless they're polyatomic ions, right? And we don't have any of that here. We just have lithium and iodine. So when I go to make this combination reaction occur, the lithium is donating an electron, the iodine is taking in an electron. Now that I2 bond, that gets broken first before that starts to happen. So that's why that 2 subscript doesn't just carry over. We want to balance out our charges: +1 lithium, -1 iodine. That should just be 1-to-1 ratio, Li(I). Now balancing, because I had 2 iodines on the reactant side, I will put a 2 in front on the product side. And then because there's 2 Li, we're going to put a 2 in front of lithium on the reactant side. So now we've got our balanced combination reaction of lithium metal with iodine solid. Now the stoichiometry, there's a stoichiometry part to this too. And the question there says, we're going to take 25.0 grams of lithium and react it with 225 grams of the iodine. And we want to know what mass of the lithium iodide solid will we make. All right, so when this happens, right, we have quantities of 2 reactants and we are asked about the mass of a product. All right, so this is a limiting reactant problem where we could go through and figure out which one is limiting first, and then take that limiting reactant, whichever one it is, to the mass of the product. The way I typically do these, because I felt like it was shorter, more efficient, is to take your A1, convert it to B, then take your A2, convert it to B, and then circle the smaller. In other words, ask the question, okay, 25 grams of lithium, what mass of lithium iodide could I make? 225 grams of iodine, what mass of lithium iodide could I make? Whichever one of those 2 reactants produces the smaller amount is the one that runs out first, and thus limits how far the reaction can go. Then next thing here is, what do I need for my conversions? Everything here is mass, so I need molar mass of everything. So starting with the lithium, I've got 25.0 grams of Li. 1 mole of lithium from the periodic table is 6.94 grams, because that's the molar mass of lithium from the periodic table. Then what I always have in the middle is my mole to mole ratio. So from the balanced equation, looking at my lithium, I have 2 moles of lithium. And on the top, going to my product side, going to my B, I have 2 moles of LiI. And then to get to grams, 1 mole of LiI, 126.9 for the iodine, added to 6.94 for the lithium, 133.84 for the molar mass. So let me go ahead and multiply, divide everything through. I get 482 grams of LiI. All right, you can probably already tell that that's not the answer, only because if 25 grams of lithium turned into 482 grams of lithium iodide, I would need like another 450 grams of the I2 to make it work, and I don't have that much, so I can already tell. The molar mass for the LiI, it should be 133.84. Let me type it. So iodine is 126.9 and 6.94 for lithium. Yeah, so 133.84. That's the molar mass for the LiI. Then the A2, now we're going to take 225 grams of the iodine, 1 mole of the I2. We just have to be careful. It is I2, so subscript of 2. 126.9 for iodine taken twice would be 253.80 grams. So there's my molar mass. Mole ratio in the middle, getting rid of I2 on the bottom, going to LiI on top. All right, so 2 LiI for every 1 mole of I2. So there's my mole ratio. And then go into the same place, so same molar mass of 133.84 grams per mole. So 225 divided by 253.8 times 2 times 133.84. I get 237 grams of LiI. All right. So for this question, I'm going to ask you 2 things. I'm going to say, kind of to repeat what we were looking at in the previous example, which one is your limiting reactant? And what is your max theoretical yield? All right. So what our calculations told us was if I had that 25 grams of lithium, I could turn that into 482 grams of product, assuming I had plenty of iodine to make it happen. But only having 225 grams of iodine, I could only turn that into 237 grams of product. So always the smaller answer is your max theoretical yield, right? Don't be thrown by max, right? Max means that's the most you can make. It's the most I can make because it told me that the I2, the limit was the limiting reactant. It runs out first. So whatever produces the smaller amount, right, the 237 in this case of the product, that identifies which one is your limiting reactant. So we would have excess lithium here kind of hanging out. At the end, it would still be in the mixture, but that's not what this question is looking for. That'll be the next question. All right, so we did our combination reaction. We took an alkali metal, reacted it with a halogen. Just remember all of those halogens, whether it's chlorine, bromine, iodine, or fluorine, they're always going to be diatomic, right? And when we combine the alkali metal and the halogen, we have a +1 -1. So those are going to come together in a 1-to-1 ratio because the halogen has a subscript of 2 by itself on the reactant side. We're going to have 2 of those ionic compounds on the product side, and then we'll balance the metal with the 2 in front.
I have a question.
Sure.
It's more on like in the conversion where the ratio is 2 to 2 for lithium and then it's 2 to 1 for iodine. Like why isn't it 2 for 2 for both? Because I don't get how it's 2 for 1 on the second one.
The reason why it's only 2 for 1 is because the coefficient is just a 1 in front of the I2. And so those are the 2 numbers that we want to pull in here, the mole to mole ratio. So basically what this is saying is 2 moles of lithium reacts with 1 mole of iodine to make 2 moles of lithium iodide. So that's why it's 2 to 1. I only need 1 of the I2s to make 2 of the LiI. Does that help?
Yeah, I got it.
Okay. All right. Any other questions there?
Actually, Professor, I had a question. So for number 5, you took like both of the substances that you were given, the lithium and the iodine, and you took them to the lithium iodide. But for number 4, like whenever it gave us the two substances, like you just put cycle instead of like actually taking it to be.
Yes. So the reason why I did that differently was the questions were asked differently. For number 4, it just asked which one was limiting. And then for number 5, it said, what mass of lithium iodide can I make? So that's why I approached them a little bit differently. Technically, with number 4, if you wanted to pick a product and just convert both of them to that product and then figure out which one was limiting, you could certainly do it that way. But that's why I did it a little bit differently, because it was just asking me for which one was limiting. So I think, okay, how many cycles can each one of those reactants do? Whereas with number 5, it said specifically, what mass of product will we make? And then it's like, okay, well then now I know what my B is, right? I know that this is what it's looking for, that mass of lithium iodide. Does that help?
Yeah, so it's just because like you don't have to go as far, I guess.
Yeah, if it's asking you the limiting reactant, it's not specifying anything on the product side. So you're right, you don't have to go as far. All you have to make sure and capture is you would take your mass of each, divide by molar mass to get to moles, and then divide by that coefficient, because they're different from the balanced equation. All right, then the next question we've got, number 6. This one says we're going to take lithium metal again and react it with water. And what are we going to produce here? All right, so this is a single displacement reaction sort of in disguise. And what always happens here, this is why these are called alkali metals, in fact, because alkali means base, right? Or alkaline or lye. And so what happens is that metal reacts with water. Remember, this is a good electron donor. It wants to be a +1 cation pretty bad. And the hydrogen actually will pick up those electrons to turn into hydrogen gas. So what happens here is the metal turns the water into hydroxide, and the hydrogen comes out as hydrogen gas. So those are the two products you always want to remember when you have an alkali metal react with water. The water turns into base, hydroxide, right? Alkali, that's where that name comes from. And the hydrogen comes out as H2. So that's how you can see that this is single displacement. The neutral lithium becomes the cation hydrogen becomes the neutral. So again, this is under the umbrella of a redox reaction. So when you go to balance this, the hydrogen looks problematic. Everything else looks good. One lithium, one oxygen, one oxygen. I've got 2 hydrogens on the reactant side, and I've got 3 on the product side. So you're like, okay, well, I need a multiple of 2. And then over here, I've got 3. How's this going to work? It's not too bad, though. We're just going to multiply the water by 2. Now I've got 4 total hydrogens. 2 of them are in the hydrogen gas on the product side. If I put a 2 in front of lithium hydroxide, there's my other 2 hydrogens. So now I've got 4 total hydrogens on the product side. The 2 in front of lithium hydroxide gave me 2 oxygens, which is good because that balances my 2 oxygens in the water molecules. And the last thing I have to do here is just balance the lithium. So I put a 2 in front of lithium on the reactant side. So for all of your alkali metals reacting with water, this is what you always make. You always make the metal hydroxide and your hydrogen gas. All right, and again, hydrogen, part of Hofbrinkel, so it's got to be H2, not just H, it's got to be H2. So we've got our balanced equation, and on this one it says if we take 25.0 grams of lithium and react it with 125 grams of water, this one says what mass of excess reactant will we have? All right, so the reason why I think this one is harder is because you don't necessarily know what to go to yet, right? That can make this a little tricky. Like in the last question, it specifically said, let's go to lithium iodide. So we knew exactly where we needed to go. This one's asking, okay, what mass of excess reactant will be left over? But I don't know yet which one's excess, right? So that's why this one's problematic. So in order to figure out which reactant is excess, the first thing I'm going to have to do is figure out which reactant is limiting. So we're going to do like what we did on number 4 earlier. I'm going to take the mass of the lithium, 25.0 grams. I always convert to moles first. So molar mass of 6.94. And then remember that reaction cycle business. For every cycle, I use 2 moles of lithium because that's what the coefficient tells me, right? I have 2 moles of lithium every time this reaction happens. So 25 divided by 6.94 divided by 2, I get 1.80 cycles. All right. Now let me do the same thing with the water. I have 125 grams of water, 1 mole of water, 18.02 gram molar mass. And then for every cycle, I have to use 2 moles of water. All right, because again, balanced equation tells me there's 2 waters every time that reaction happens. So if I take the 125, divide by the 18.02 and divide by 2, then what I get here is 3.47 cycles. So like we talked about with number 4, the 1.80 is the smaller number. So that tells me that lithium is going to be my limiting reactant. So how far this reaction goes is dependent on the lithium. We already know that water is going to be excess, right? Because if lithium is limiting, then the water is going to be excess. So when the question says, okay, what mass of excess reactant is left over? Really what this is saying is what mass of water is left over. All right, now we figured out, right? What is our excess reactant? The water, because lithium is limiting, so the water is excess. So when the question says what mass of excess reactant, that means water would be left over when this is done. So then the next thing we have to do is figure out, okay, how much of the water would we use, right? If we know that lithium is limiting, how much water will react with the 25 grams of lithium? All right, so that'll be our next thing that we want to do. So we had 25 grams of lithium, molar mass, 6.94 grams. Mole ratio in this case is 2 to 2. For every 2 moles of lithium I react, I have 2 moles of water. And each mole of water has a mass of 18.02 grams. So this calculation will tell me how much of the water I actually use. And to 3 significant figures, I get 64.9 grams of water, and that would be used. So not done yet. One more step. How much was not used? Well, we had 125 grams of water to start with. That was given to us in the question. And we know we used 64.9 grams based on our calculation. If I follow my decimal place rule, right, I'm going to have to go just right to the ones place. So when I go ahead and subtract everything through, I get 60.1 grams, but we're going to round that to 60 grams. And we want to put the decimal on there because we want to show that the 0 is a sig big. And the reason why I cut off the 0.1 is because we were following the decimal place rule. So 125 goes to the ones place. So my final answer here should go just to the ones place. All right, so those excess reactant questions are certainly longer because, again, it's like you're not even being told what you're really asking for. You just have to figure that out first. So if you're being asked about the excess reactant, find which one's limiting first, doing that same thing we did for number 4 earlier. Now that you know which one is limiting, take that and figure out how much of the other reactant you would actually use. And then say, okay, well, if I started with 125 and I used 64.9, that means I would have 60.1 left. And then of course, follow your decimal place rule. All right, so those definitely, I think, take a little bit more time. All right, and then I've got one more planned on the review. Another stoichiometry question. All right, so this is number 7. So number 7 says we want to do the balanced equation of lithium metal, another alkali metal, in this case with oxygen gas. All right, oxygen again, part of Hofbrinkel, so it's got to be O2 when it's in its elemental form. That's the thing. All right, now it's another combination reaction. The lithium and the oxygen are going to come together. That's going to make an ionic compound. So I need to think about charges. Lithium will become the +1 cation. Oxygen will become the -2 anion. And then if I crisscross here, I should get Li2O for my final ionic compound of the lithium oxide. Because I have 2 oxygens on the reactant side, diatomic, the Li2O, I need to multiply that by 2. So that balances my oxygen. Then 2 times 2 is 4. So I'd have a 4 in front of the lithium on the reactant side. So that's what happens when you take your alkali metal and combine it with oxygen gas. And you make that alkali metal with oxygen in a 2-to-1 ratio, and then you just have to balance it out. So we've got our balanced equation. This one says, and I'll write it out, what is the percent yield if 25.0 grams of lithium reacts with 125 grams of oxygen to produce 45 grams of the lithium oxide solid. All right, so for this question, this one, you just have a lot of numbers, right? What is the percent yield if 25 grams of lithium reacts with 125 grams of oxygen to make 45 grams of lithium oxide? So I think sometimes what students struggle with here is like, okay, what do I start with and where am I going? Because you've got numbers for everything, and that can certainly make it more complicated. So what I always say is, okay, if you're looking for a percent yield, we know the formula is the actual yield over the theoretical yield, and then percent parts per 100, so times 100. Now, in lecture class, the actual yield is not something we can come up with. If we did this in lab, we could do that, right? We could do the experiment, we could get the actual yield, but in lecture class, that has to be given to us. So when I look at those 3 numbers that were given to me in the problem, one of those is just there because it's my actual yield, right? And so then that helps me say, okay, one of those is just going to be for my percent yield problem at the end, just figuring out percent yield. Now, the other thing I always want to mention is if you're doing a percent yield, right? It's a yield, not percent consumption, but a yield. You're always going to find the percent yield of a product. Always, right? So that means I only have one product here. I'm finding the percent yield of the lithium oxide. So that means that that mass of lithium oxide, that must be my actual yield. So when I go to determine my percent yield, I'll have my actual 45 gram mass of lithium oxide. Then what I need to do is figure out what theoretical mass of lithium oxide should I have made. So what this helps me understand is the 45 grams I pull out, I'm going to put that in my percent yield formula, save that for later. And then it also tells me if I have the actual yield of lithium oxide, I need my theoretical yield of lithium oxide. How much was I supposed to make? I know I made 45, but how much was I supposed to make? So then I'm going to take my 25 grams of lithium, figure out how much lithium oxide that would make. Then take my 125 grams of oxygen and figure out how much lithium oxide that could make. All right, so I still have a limiting reactant problem because I have quantities of both of my reactants. I got to figure out which one runs out first. All right, so I've got first my 25.0 grams of lithium, 1 mole, 6.94 grams. Mole ratio comes next from the balanced equation. 4 moles of lithium will make 2 moles of Li2O. And then for 1 mole of Li2O, 6.94 taken twice and then added to 16 for the oxygen. I get 29.88 as the molar mass of the lithium oxide. So when I multiply and divide everything through, I get 53.8 grams of lithium oxide. All right. Now I need to start with the mass of the other reactant, which is 125 grams of oxygen. 1 mole of oxygen is 32.00 grams. In this case, the mole ratio from the balanced equation, for every 1 mole of O2, I make 2 moles of Li2O. And then molar mass is the same, 29.88 grams per mole of Li2O. So 125 divided by 32 times 2 times 29.88, I get 233 grams of Li2O, right? Which obviously I can't make that, right? I don't have enough lithium to do that. The lithium can only make 53.8 grams. So that's going to be my max theoretical yield, right? In theory, if everything's perfect, that's what we should get. Whenever we use these constants, right, from the periodic table, that these are perfect numbers, everything's perfect, we should get 53.8 grams. Question told us though, we only got 45 grams. So last step here to determine my percent yield, I produced 45 grams of Li2O. According to my calculation, I should have produced 53.8 grams of Li2O. So what is my percentage? 45 divided by 53.8 times 100. And what I'll do here is check my sig figs. I should only have 2 sig figs because of the 45. And so I would round this to 84% for my percent yield for this particular reaction. All right. So for the review today, what I tried to do was a little bit of all of our stoichiometry, a little bit of all the different equation types that we had. So the combustion and then the 3 reactions of alkali metals, first with the halogens, then with water, then with oxygen. We did combustion. We did empirical molecular formula, percent composition, a little bit of everything in terms of mass, moles, molecules. So I think for this first test, if you were me, the hard part would be the nomenclature. That would be the part that I would have to go back and study. But I will say that the grades for quiz 2 were very good. So you guys are probably better at memorizing things than I was back then. But if anybody wants a little review on nomenclature, we can certainly do that. Anybody have questions for me? But those were the review questions I had planned for today. But of course, we have time. I can answer any other questions you have.
Professor, just going back to the, I'm sorry, did I interrupt something?
No, go ahead, Sal.
Just going back to that previous example we did for 233 grams, why did you say we couldn't make that?
Well, what we know from our calculation is the 25 grams of lithium can only make 53.8 grams of the product. And once that mass of 53.8 grams of product has been made, the lithium is gone. It's run out. So we don't have enough to get to 233. We can only get to 53.8.
Okay, I see. Thank you.
Yeah, you're welcome. Scott, were you in the process of asking a question?
Yes, ma'am.
Okay.
Question. I missed some of these equations breakdown. I did see that we're recording this. When will it be posted to review?
It will probably take about 10-15 minutes afterwards because my computer has to, yeah, it just converts and then I have to get it on YouTube and then YouTube has to process it. And then sometimes YouTube takes a while, but it's usually not very long.
Perfect. Thank you so much.
Yeah,
this is very helpful.
Good. Anything else anybody wants me to go over? Austin.
Yeah, so for number 6, whenever you took the lithium, I guess, or so after you figured out the cycles and everything, I guess, you took the lithium to water. I was just confused because it was asking the mass of the excess reactant. I guess I was just confused on instead of taking it to B or whatever, how we were doing it, you just took the lithium and took it to water.
I know I do think that these are more complicated. And again, that's kind of what I was saying. A lot of this is really familiar from intro, but then all of a sudden we throw this in and we were like, oh, we haven't done this. We didn't do this in intro. The idea, the kind of my thought process is that when the question says what mass of excess reactant you will, that's because that's what the question specifically said, what mass of excess reactant. So when you see that, what mass of excess reactant, the problem with that is that you don't know what the excess reactant is, right? So you're being asked for the mass of something that you don't even have, it's not identified yet. But if it's a reactant, right, it has to be either lithium or water, right? Those are my two reactants. One of them will be limiting, one of them will be excess. It would be really nice to look at these numbers that we're given, the mass numbers, and just say, obvious, lithium will be limiting, but it doesn't always work out that way. So you really have to go through the calculations and first figure out, okay, yes, one of these is excess, but that means the other one is limiting. So that's what I do first. I try to figure out which one's limiting. And that's the process that we did earlier. We have mass of each reactant. We go to moles using molar mass from the periodic table. And then just don't want to forget to capture the difference in those coefficients, right? In this case, they were the same. So if we forgot that step, we'd get lucky. But we're not always so lucky. So we divide by that coefficient. This tells us how many cycles, right? It's kind of generic, but how many reaction cycles we could do. The lithium has enough to go through 1.8 cycles. The water could do 3.5, right? So it could really keep going, but we don't have enough lithium to do that, right? Once we do the 1.8, the lithium runs out, reaction comes to a stop. So now if we go back and read the question, and it says, what mass of excess reactant? Well, now we understand if lithium is limiting, then that means the water is the excess. So now we know what this is actually asking us. It's saying, okay, what mass of water would remain? So when I look at this, that's what I did here. It's like, okay, we determined lithium was limiting. So that means water is excess. So what mass of water is left over? So now at this point, I know this seems weird, but your water is really your B. It's where you're headed. And your lithium, because that's the limiting reactant, is where you're starting. So the thought process was, okay, we had 125 grams of water. We're not going to use all of it. How much are we going to use? So we start with the limiting reactant that limits how far the reaction can go. And we convert it to the mass of the second reactant that we would use. And what our calculations told us was, if we start with 25 grams of lithium, we're going to use about 65 grams of water. Okay, one more step. If we had 125 grams to start with, but we only used about 65 with the lithium, that means we had 60 left. So that is the kind of long process to figuring out mass of excess reactant. And again, the problem is if it says what mass of excess reactant, you don't know what the limiting reactant is yet. So that's why it becomes very problematic. Does anybody want me to do one more just to kind of run through it? Because I can do another I can do another example if y'all want me to.
Yes.
Okay,
Yes.
let's do another one. All right, so I'm going to use the same equation that I have over here. So just because it's right here, I got 4 lithiums reacting with my O2 gas to make 2 moles of lithium oxide. All right, so question is, what mass of excess reactant is left after 25.0 grams of lithium combines with 72.5 grams of oxygen? All right, thank you, Scott. Okay, so one more example here. We've got our balanced equation. And again, when it says what mass of excess reactant, when you see that, it's a little bit of like, oh, I've got a lot to do. Because again, it's not telling you what we're looking for. I mean, it's sort of vague, right? I know if it's looking for the mass of a reactant, I'm looking for either lithium or oxygen, right? But I don't know which of those 2 reactants is excess yet. So I'm starting with 25.0 grams of lithium and 72.5 grams of the oxygen. And the only thing I will say about this is I know that nowhere in my calculations am I going to need the Li2O because I'm only focusing on the reactants here. So I'm only looking at the lithium and the oxygen. So the idea is that I'm going to put this 25 grams of lithium into my reaction vessel. And then I'm going to add the 72.5 grams of oxygen. And those two things, they're going to react and react and react and make product. But eventually the reaction stops because one of those reactants runs out first. So that's actually my first question is which one runs out first, right? Because that's going to say how far the reaction can go. So like we did before, I'll have my 25 grams of lithium. Always go to moles first using molar mass 6.94. And then the limiting, right, is looking at sort of reaction cycles. For every cycle, I need 4 moles of lithium. All right, so that first calculation, again, is just telling me how many reaction cycles the lithium could do. So if I have 25 grams and I need 6.94 grams per mole, and I need 4 moles per reaction, I have 0.9, sorry, 0.01 cycles. All right, sorry. Then the second part is I have 72.5 grams of oxygen. 1 mole of oxygen, 32.00 grams. Again, don't forget it's diatomic, so we got to take into account both oxygens. And then for each cycle, I only need 1 mole of O2. Just capturing that the coefficient there is just a 1. So if I take 72.5 divide by 32, I have enough to do 2.27 cycles. All right, so again, all this is telling me is which one is my limiting reactant. Whichever one produces the smaller amount is my limiting reactant. So the lithium is my limiting reactant. And what that means is my excess reactant is going to be the O2. So now if I go back up to the question, it says what mass of excess reactant? Really what this is saying is what mass of O2 is left after the 25 grams of lithium combines with 72.5 grams of oxygen. So all I was able to do with that first calculation is just identify what my B is, right? I'm going to start with my limiting reactant, which is the lithium, and figure out the mass of oxygen that I would use. All right, the 72.5 is not a starting point anymore. What I'm going to try to figure out is the 25 grams of lithium, how much oxygen do I have to combine with that? All right, so that's my next step. So let me move my paper. I'm running out of room, so let me go to the next page. Okay, so then step 2 is to figure out mass of oxygen that I'm going to use. All right, and you want to start with the limiting reactant, so 25.0 grams lithium, right? Because that always tells you how far this will go. The limiting reactant tells you. Going to moles first, using molar mass, mole-to-mole ratio, getting rid of lithium, going to O2 from the balanced equation, 4 moles of lithium for every 1 mole of oxygen. And then to get to mass, 1 mole of O2, 16 taken twice, 32.00 grams. So if I start with 25 grams of lithium, divide by 6.94, that means I had about 3.6 moles. I need 4 moles of lithium for every 1 mole of oxygen, and then times 32 to get to grams. I would use 28.8 grams of oxygen. So that would be how much I would use. That's the mass of oxygen I need to combine with 25 grams of lithium. All right, and again, the lithium that we found was the limiting reactant. And we went to O2 because that was the excess reactant. So that's always the process. Like when you're looking for the excess reactant, you have to figure out which one is limiting first, then start with that limiting reactant and figure out how much of the excess reactant you will use. Now, if I go back into the question, it says what mass of the O2 excess is left after the 25 grams of lithium does its reaction. So I started with 72.5 grams of oxygen, and I used 28.8. So how much would be left, right? We're just going to take the difference and follow our rules, which are the decimal places. And so that would tell me I had 43.7 grams of oxygen left over. So basically what happens, what we figured out here is, if I can kind of draw this out, we had our lithium, 25.0 grams, reacted with our O2. We had 72.5 grams, and we made our product, the Li2O. And what happened was, is this reaction, we found out that the lithium was limiting. And what that means is this reaction will go until the limiting reactant runs out. And then as soon as it runs out, the reaction has to come to a stop. And what our calculation up here told us was that if we had 25 grams of lithium reacting, we consumed 28.8 grams of oxygen. So the 25 grams of lithium combined with 28.8 grams of oxygen to make this product. So we didn't use all of the oxygen, we only used 28.8. So when we subtract, what that tells us then is 43.7 grams of O2 oxygen would be left over. It would still just be sitting there. So all of the lithium would be gone. We would have our product mass, and we would have 43.7 grams of oxygen still left in there. So that's what we're trying to find out when we do mass of excess reactant. It's sort of a longer process. You got to figure out which one's limiting first, and then take your limiting to your excess reactant to figure out how much you've used, and then subtract that from what you started with to figure out how much is left over. All right. Any questions on that example?
No, all good. All good.
Okay. Thanks, Ramon. Appreciate that. Anybody have questions on anything else?
So I think I get the excess reactant now, but I guess one thing that like kind of threw me off whenever I was like doing the practice quizzes and stuff back in like for chapter 2 or like nomenclature is whenever like it was like asking us like, you know, like, okay, metal, non-metal, acids, all that, whatever, but like I guess it came to like the last couple questions on the practice quiz. Whenever it gave us 3, it was like the hydrates or something. Is that going to be on the test?
The hydrates might be on the test. The thing that was causing trouble with the hydrate, and I didn't mean this. It's like, it's such a random thing that you don't think of until it happens. So just as an example, let's say, I think one of them was like, oh, and now it decides to freeze. Hold on. Sorry, Austin. Where like it'll give you the name, and it'll say something like iron 2 sulfate, and then heptahydrate or something like that. So what I think some students did is they took the practice. Yes, the dot was another problem too. The iron 2 sulfate, right? Iron 2 means Fe plus 2. Sulfate means SO4 negative 2. Hepta means 7, and hydrate means water. So the only thing we have to really worry about here is balancing the charges on the ionic compound, just like we did without hydrates, right? Like you take this part out of the equation, and just like we practiced in intro chem, if I've got a +2 cation and a -2 anion, those are just going to come together 1-to-1. And then there's a little dot, and then the 7H2O, but the little halfway dot is not really something that's easy to type in. So a lot of students just did a bottom dot, like a period. That's all. It's obviously all fine, right? Some of them left them out altogether. Some put a space in, some didn't put a space in. And the system, of course, is very picky. It's just looking for FeSO4 dot 7H2O. So if you have a different dot, no dot, a space, no space, it's going to mark you wrong. So I have to just go in and fix it. It's not the end of the world. So that's why I always say, like, when you get your first score, don't just completely ignore it, because especially on this quiz or test, sorry, on this test, there's a lot of written response questions. And I have to grade those. They are not automatically graded. So those start out as 0 points. And then I go in and grade them and give them the points that they deserve. So definitely do not look at your first score, right? So once they're all submitted by tonight, tomorrow and Thursday, I will get them all graded. It will take me a little while because I do prefer to have some written response questions, even though that takes it longer for me to grade. And that means you have to have more patience to get your final score. And I apologize for that. But I like it when students sort of show me what they know, right? And that's multiple choice doesn't always do that. Is there going to be an X number of hydrates problem? Like, you mean how many of these would there be? I think there's maybe 1 or 2. It's not a bunch, but there will be 1 or 2 of the hydrates. So this was a new thing. We didn't really do this too much in intro. The hepta, those are the same as those binary covalent compound prefixes. So hepta means 7, hydrate means water. And then the other thing is I noticed on the practice quiz for this, when students saw the answer key, the answers are always given in parentheses. So then the student would be like, oh, okay. And then when they would enter in their answer, they would put it in parentheses. And you don't need the parentheses. That's just the system. When it gives you the answer, it always gives answers in parentheses. So, but you don't give your answer in parentheses. Anyway, it's confusing. It's all just something I can go in and fix it. Okay, thank you, Christina. Anyway, I hope that was helpful. Anybody else have like some questions for me? And the practice quizzes, sorry, Ahmad, I'm so sorry. I just thought of this. The practice quizzes, they stay open for the whole semester. So if you want to go back in and take those, even if you're like, you know what, I don't want to worry about my score. Don't worry about that. The highest score is always recorded. If you just want to take them just to take them, you can take them as many times as you want. Ahmad, now I'm sorry. What was your question?
No, it's all good. So all the conversions we did throughout this, is that pretty much the bulk of what we need to understand how to do in terms of converting and like stoichiometry and stuff? Because I kind of struggled with, I believe, like the chapter 3 quiz. I believe I struggled a little bit with the conversion, so I wasn't sure. I mean, I'm having a hard time remembering exactly what the questions were, but like, is that like okay with everything we've done so far? Is like that's what the bulk of what we need to know in terms of conversions?
I think with the conversions with chapter 3, that was where we started our mass, moles, molecules, and then some stoichiometry. I think stoichiometry was more in module or chapter 4 though. What I would suggest if you can is go look at your practice quiz for chapter 3. And like now that we've done the review, see if you still have questions on it, and then email me if you have any questions on it, or try taking it again and see if your grade gets better. But yeah, definitely that will be on the test.
Okay. And so how if I have any questions and I would like to email you, do you know like approximately like how long you'll be available for day before the exam? Like when it would be like the last time to get in questions before?
Yeah, I go to bed kind of early because I get up really early. So I can answer emails at 5 in the morning, but that's not going to help you. So I usually shut it down around 9 o'clock.
Okay, thank you.
You're welcome.
I didn't actually, Julie, I didn't hear what you said. It cut off. I don't know if it was internet connection about the conversions, like what we have to have memorized. Was it just real basic ones or?
The conversions, I tried to identify those, like the unit conversions. Those are the ones in the chapter 2, 3, or sorry, chapter 1 notes. In the chapter 1 notes, I write, okay, those are the 6 prefixes, and then those are the conversions that you want to remember for the first chapter 1 unit conversions, and then also the temperature conversions. So like Celsius to Fahrenheit, etc. I think with the stoichiometry part, I don't know if there's anything necessarily to memorize there. I never looked at it that way, but I would say memorize Avogadro's number, 6.022 times 10 to the 23rd. But other than that, I don't think there's anything else to memorize. It was mostly just go ahead, sorry.
The polyatomic ions I saw was on there.
Oh yeah. So in terms of formulas, I think that's it. But yeah, your polyatomic ions, you want to memorize those. That would be the hard part for me.
Yeah. I need flashcards.
Yeah, that's good. Flashcards are very good.
So you said like in terms of like formulas and stuff, the only things that like we didn't need to know, like any of the like, because I know that the list of like conversion factors, it was like 2.205, like the number conversion factors other
Right.
than like the nano, millicenti, all those.
Yeah, so you need to know your 6 prefixes and then those 4 conversions that we had in the chapter 1 notes, but that's it. So like if there's something that has pints or ounces or something like that, you don't have to memorize those. That would be given to you if you need it.
Okay.
All right, all good questions. Anything else?
Oh, so I guess like because the review was just a bunch of like stoichiometry, is that like mostly what the test is gonna be on, or like,
Oh,
or is it gonna be on like everything?
I don't want to say mostly. I think it's pretty evenly distributed between stoichiometry. Nomenclature is a big one. It's just a big part of the unit. Nomenclature is big. And then there will be unit conversions and density and stuff from chapter 1. So I really do try when I write the test to go through all of the chapters and kind of break it up equally. This many points for chapter 1, this many for chapter 2. The reason why I did the bulk of the review today with stoichiometry was so that I could review equation writing and mass moles, molecules, and all at the same time. And there's a lot there: limiting reactant, excess reactant, percent yield. There's a lot to do there. I feel like with chapters, and this might be my own bias, but I feel like with the chapter 1, chapter 2, chapter 3 material, just based on what I saw with the quiz scores, it didn't seem like students needed quite as much review with that, whereas chapter 4 might have been a little bit harder. I don't know. So this might have been my bias for today with what I presented. So I would say it's equally distributed over the 4 chapters. So I wouldn't say only look at stoichiometry. I think you want to look at a little bit of everything. Does that help, Austin?
Oh yeah, thank you.
Okay, good. All right.
Professor, going back quickly on the prefixes, when for intro to chem, we didn't express the prefixes in the same manner. Is that right?
Yes, I would agree with that.
What, it's like for the exam, is it all, like, how should we have to express it? Does it matter which way?
No. So if you're doing a conversion, so like just as an example, let's say I had 275 milliliters and I want to convert it to liters. So the way that we express this in intro, right? We said 1,000 milliliters in a liter, right? And we got our answer and we were done. The way that this is now is they say, oh, no, now what you do is you say you have 1 milliliter, and that's the same as 10 to the negative 3 liters, right? Because milli is 10 to the negative 3. I will take either way. If you're more comfortable with the 1,000 milliliters in a liter, do it that way. If you want to do it the book way, where you replace milli with 10 to the negative 3, do it that way. But I'll take either one. So either that way, 1 milliliter is 10 to the negative 3 liters, or the way we did it in intro. All right. So if the system says, oh, well, that's not what I had, but it's the right answer, I'll go back and fix it. You pick which way you like better.
Okay. Yeah, I like the way that we did an intro better, probably because that's what I was used to from last semester.
Yeah, and I think that's typical. I think a lot of students are right there with you.
Okay. Okay, thank you.
Yeah. All right, we are at 12:33. Nope. One more question.
Yeah, I was gonna say, like, so with chapter 3, I understand, like, when we're doing conversions, that like what we want to go to the top, what we want to cancel out's on the bottom. I just don't know why I struggled so hard with any questions in chapter 3. Would you be able to do an example from chapter 3? Anything from the quiz that we did, for example, like any kind of formatting where we're just understanding the placement of what we're trying to go to, like where we're trying to end up?
I think yes. So for chapter 3, big thing here was, so let's say, and I'm going to use sort of an example I had earlier. We had copper 2 chlorate, and then we had the tetrahydrate. So this was the first example we looked at. And the reason I'm doing this is the molar mass is already here. So the molar mass is 302.53 grams. So what I did in the review when we started is we went sort of piece by piece. We had a mass of the copper 2 chlorate tetrahydrate. We figured out moles. Then we went to molecules. Then we went to atoms. And in chapter 3, instead of breaking them up step by that, I sort of just went all to the end point. So let me do one like that. Let's say I've got 125 grams of the copper 2 chlorate tetrahydrate. and I want to know how many hydrogen atoms are in that sample. Sorry, that A came out kind of wonky. All right, so I have 125 grams of the copper 2 chlorate tetrahydrate. And we know the very first thing we always do is go to moles. And so we have our 302.53 grams, and we would go to moles. But here's what's going to look a little weird, I think, in the chapter 3 conversions is you're only given 2 conversion steps, and it kind of looks like you need 3. And so here's why you only have 2. We can go to 1 mole on top, and then 1 mole is Avogadro's number, but because we'd have 1 mole and 1 mole, right, those would cancel out. So it's sort of like if A equals B and B equals C, then A must equal C. So your molecular weight from the periodic table is equal to a mole, which is equal to Avogadro's number. So what we have is we got grams on the bottom to go away. And then on top, we'll have 6.022 times 10 to the 23rd molecules. And we know they're molecules because the copper 2 chlorate is a compound. And then one more step here, for each molecule of the copper 2 chlorate, how many hydrogen atoms do we have? And what we would look at here is we have 4 times 2. So we have a total of 8 hydrogen atoms per molecule. So in terms of chapter 3, not doing mole ratios, right, just yet, just sort of looking at those molar mass, Avogadro's type conversions. And this one, we've got a compound and we're breaking it down to atoms. So we take our mass, right, technically to moles first, but mole and Avogadro's number, those are interchangeable. So 1 mole is 6.022 times 10 to the 23rd. And then for each molecule, looking at the formula, 4 times 2, there'd be 8 hydrogen atoms here. So if I take my 125, divide by 302.53 times Avogadro's, and then times 8, I get 1.99 times 10 to the 24 hydrogen atoms. All right, let me scoot that over a little bit. All right, so that was sort of more like what we saw with chapter 3. But what I would recommend if you have a chance is either try the chapter 3 practice quiz again, or at least look at your submission and see if you have questions on it, and then just let me know if you have anything. But otherwise, I actually have a student waiting for me to take it to a different test at 12:30. So I have to probably call it for today. But any last minute questions I can help anybody with?
Miss, I was just wondering, can we use probably it's not a good question, but can we use paper to like do calculations in the test?
Yeah, you have to have scratch paper. Ideally, what you would do, like this is the only thing I don't love about teaching online is the testing aspect. Ideally, what you would do is when you do your room scan, when you get into honor lock, is if you have scratch paper, you would hold up the scratch paper to the camera and just show me front and back. That would be ideal.
Okay.
Yeah. But yeah, I think you'll need a couple pieces of scrap paper. I would. I can do
Right.
some things in my head, but not too many things at once. Not anymore. All right, Sal, what about you?
Professor, just for the calculator, it'll be provided as it was in the intro, or are we going to use our own?
I would rather use my own personally. So I've put it on there that you can use your scientific calculator.
Okay.
So that, I don't know. I can click on the computer, but I prefer to use my calculator.
Okay.
All right.
Thank you.
You're very welcome. Any other questions for me? All right. I wish you guys a great day, and I will get this posted shortly. Thank you. Have a great day.
Thank you. Bye-bye.
Bye.